Hey everybody, in this video I'm going to show you the math behind RC circuits, and we're going to derive functions for charge and voltage and current through a capacitor for charging and discharging cases. So if you recall, when you were experimenting with RC circuits, the first thing you did was to charge the circuits, and I'm going to just start off by sketching a few graphs that should look familiar to you. For example, if you were to look at the charge across the capacitor as a function of time. So this is when you have the battery and a capacitor and a resistor, and you close the switch for the first time. You would see that the charge increases and looks something like this. Okay. The other thing on the capacitor is the voltage, and the voltage also follows the same pattern. So what I'm going to do on my graph here is I'm just going to put a comma, and I'm going to say that voltage does the exact same thing. So these two quantities, charge and voltage, both indicate the charge and voltage for the capacitor. And both of those things increase as you charge. Now, when you're charging the capacitor, there is something that decreases, and that is the current through the capacitor. So we call that I. And the current actually starts off with something, and then it drops off in this sort of a way. Okay. So that's something that you observe. Now, I'm using a lowercase I for the current, and I was using a lowercase q for the charge in the capacitor. And the reason for that is it's kind of like the convention that when you have something which is changing, then you, as a function of time, you just use a lowercase variable. I guess the same thing is true for the voltage, although it's kind of hard to tell that it would be lowercase. All right. When you discharge the capacitor, I hope you observed that basically everything in the capacitor is going to drop off, sort of like this. So charge on the capacitor goes down, the voltage across the capacitor goes down, and the current goes down, all in the same way. So you might be suspecting or suspicious that these curves are actually exponential curves, and in fact, you're correct. And you might have even noticed that there is an asymptote, right, for this one here. You probably saw that in the simulation. And of course, in the bottom ones, there's kind of an asymptote of 0, right, as time goes on. So what I'm going to do is just tell you what the answers are first, the functions, and then I'll derive them for you. All right, so in the first one, if we come up to charging, we're going to say that the charge is going to be some function of time, and I'm going to put down that that function of time is going to be equal to q times 1 minus an exponential to the negative t over rc. Now, that q that's there is actually the final charge on the capacitor. So if you like, that's going to be equal to the EMF times the capacitance. Remember that voltage times capacitance gives you charge. So this is the final charge. That's why I'm using a capital Q, because it's kind of a fixed value. The voltage across the capacitor also is going to look like this, okay? Except now we use the EMF for the battery, but we have exactly the same thing in parentheses. So do you see in parentheses where the time variable shows up? Right, that's important to keep track of. So here's your function of time right here. Here it is again. And you also see that you happen to be dividing by the same thing in both cases. So you're always dividing by RC. And that's important, and we'll talk about why you do that later on. But again, the EMF, the EMF symbol, that's the battery voltage, right? And the big Q stands for the final charge across a capacitor, which you could just calculate the usual way. But this 1 minus e to the negative, right, 1 minus a negative exponential gives you this shape. And hopefully you remember that from math class, or you could just try to plot it really quickly on your calculator to see it. Now, for the current case, again, following our assumption, we say that I, lowercase I, is going to be equal to something, right? But this is going to be a simpler function because it's basically just kind of decaying. Now I'm going to leave some space in front here, and I'm just going to write this for the exponential. I'll have my negative t, and again, I divide by this RC. Isn't that neat? It keeps popping in. And what comes in front, right, would be whatever you put in front here, this term, that's kind of like your starting point here. That would be kind of like your initial current, I0. But we can do better than that. We know that the initial current in the circuit is basically just the current that would flow through the resistor. So I'm going to use Ohm's law, and I'm simply going to use that for my initial current. All right, is everybody, you with me here? So remember, Ohm's law says that current is equal to voltage over resistance. Just a reminder, right? And in this case, our voltage is the battery voltage, and the big R is going to be the resistance of the circuit. That's the load resistor, the resistor you have in the circuit. So once again, if you want to highlight this, you've got the RC, again, showing up down here. And again, you've got this time function. So very similar forms, all exponential functions. It's just that you've got one minus in the top and then just a straight up negative exponential decaying in the second one. For the discharging cases, this is really fast and easy because all of the functions are going to be decaying. And so what you can do with this is you could probably almost guess that. In fact, if you want to pause the video and guess, go for it. But I'll go ahead and just write them. Okay, that's going to be your initial decaying function for discharging, right? Then for voltage, you'll have the EMF, which is doing the exact same thing. And for current, you're going to have that initial current, again, times the decaying exponential. So these three functions, of course, all go with this last graph, right? Whereas if you look up on the top, that function was the only decaying exponential for current, and these two were going to be the exponentials approaching an asymptote. Okay, so you have to know this. This is an important thing. RC shows up. You're always dividing by RC in the argument of the exponential. And you always have to pay attention to what's multiplying the exponential. And that's all important stuff. So let's see where that comes from, okay? So let's go on and derive this, okay? So we're going to derive it, and I'm going to draw the circuit as compactly as I can, okay? And I'm going to do the charging case, okay? I'm not going to derive the discharging because if you get the charging, you're in good shape. So this is the EMF of the battery. This is the resistance of the load that you put into the circuit. This is the capacitance. And as soon as you close the switch, what happens is that the battery, being positive on this side and negative on this side, it starts to push current in that direction, okay? And that has the effect of making the side of the resistor closer to the battery positive and the side of the resistor further from the battery negative. So there's a potential loss as current goes through the battery. It's consistent with Ohm's law. The other thing we know is that when you push current this way through a capacitor, you get pluses that build up on this plate, which is close to the positive side of the battery, and you get negatives that build up on the other side. And so that's important to think about, right? So the current loops around, it happens, it takes a few seconds, and then eventually the capacitor gets all filled up. So let's write basically, let's sum up the voltages around this loop. So we're going to sum voltages, I'll just say volts, around our loop. And we haven't necessarily done this way before, but I'm going to begin just by writing something here and then try to explain it. I'm going to start off by writing the EMF minus the current times the resistance minus Q over C is equal to 0. And we're going to take a minute or two just to talk about that. Okay, so let's talk about it. So first of all, the first term here is the battery, right? You could even put a plus in front of there if you want. But that's where the voltage is coming from in the circuit, right? You're getting the voltage from the battery. That's their push on the electrons. It's the energy, right? Now, as you go through the resistor, you're going to lose some voltage, right? you're going to lose some voltage. And so maybe another way of writing this, maybe I should have started with this, is just you're going to lose voltage across a resistor. And that's where IR comes from, right? Because Ohm's law says that voltage is equal to I times R. Now, you're also going to use up voltage on the capacitor. And that's where the Q over C comes from. See, that's like subtracting the voltage across a capacitor. And all those voltages have to add up to 0. By the way, if you're not sure about Q over C, just remember that capacitance is Q over V. And so if I rearrange that, I get V is equal to Q divided by C. And so that's where that comes from up here. So this is a rule in electricity. It's actually energy conservation. These statements here are both E conservation, because it says whatever energy you start with, right? Whatever energy you start with here is completely consumed or used in other parts of the circuit. In this case, in the resistor and in the capacitor. All right, it's stored in the capacitor, and it's kind of turned into heat in the resistor, right? So chemical energy in the battery turns into heat in the resistor, and then it turns into stored energy in the capacitor. So this is basically our starting point. This is a really important statement right here. Now, the rest of what I'm going to do is basically I'm just going to write this. This is actually an equation to solve, and I'm going to have to solve it. I'll solve for Q as a function of time. So I'll put a t in parentheses, but that means as a function of time. And this is actually going to be what we call a differential equation. I'm just going to put diff EQ, right? Differential equation, which may sound scary, but it's really not too bad, and it's all calculus that you've done in calculus already, or I can show you pretty easily right now. Okay, so I'm going to start off, and I'm going to move some terms around here. I'm going to take the IR term, I'm going to bring it out in front. Hey, and I made it positive too. So that means I multiplied everything but through by -1. So after that IR term, I'm going to have plus Q over C. And then since I did the negative thing, I'm going to have minus EMF is equal to 0. Okay. Now, you might be wondering, well, why did he do that? What's the reason for doing that? And here's the big hint that we're going to build up to, right? Is I'll put a note here, is that this I that's right here is actually a derivative. It's the rate of charge changing in the capacitors, dq dt. And what I'm really setting myself up for in the next few lines of algebra is I want to solve this differential equation where I've got the dq dt, so I'll circle it, and I have a q here, and that's going to let me solve for the q that I want. So the next couple steps are going to be a game where I just try to get that q, I try to separate these variables out, and I get the q by themselves, okay? So just bear with me, okay, and follow along. The next thing I'm going to do then is going to take the I, I'm going to divide both sides by r. I'll divide both sides by r. So if I do that, I get rid of the r in the first term, but I end up with 1 over RC in the second term. See what happened there? I'm writing it out in front. And then I have to divide r by the EMF on this side. And that's all equal to 0. Okay. And you might be wondering, like, hey, does this work out dimensionally? But hint, hint, it does. Look at that last term, voltage divided by resistance. That's current. And that's the same as the first term. And in fact, you could show yourself it's even the same dimensions as the second term too. So that's a good thing. But you don't have to see that right away. All right, next thing I'm going to do is I'm going to combine the second two terms with a common denominator. See these two terms. So I'm going to write this, I plus, and then how do I do this? I've got Q over RC, but I also want to combine the, get the second term into that. So I have to multiply a C by the top and bottom. So I end up with this. Okay, a little bit of algebra there. So I have a common denominator. And again, just bear with me for now, and you'll see why this happens in a little bit, or why we're doing it. Okay, then what I do next is I'm going to bring that term over, okay, to the other side. So I subtract it. I'm going to write it like this. right? Check my algebra. I had to subtract the term to get it onto the right side. That's where the negative comes from. And then I just pulled that 1 over RC out in front. Okay. And now I do the magic of separating variables. So this I, right, is actually equal to dq dt. And so what I'm going to do is I'm going to leave the dq on the left side, but I'm going to move the dt over here. Okay. And then I'm going to take this stuff with the q in it, and I'm going to have to move it back over next to the dq. This is called separation of variables. So sep of variables. It's a technique for solving a differential equation. So I'm going to end up with dq over q minus that is equal to negative 1 over RC times dt. And this is something you can do in calculus, is you can split up the dq dt into two parts, and you can treat them like as algebraic things, symbols. Now, the reason that we do that is because, hey, we now have, we basically have our differential equation, right? We have an equation where you've got a dq on the left, a dt on the right, and you want to solve for q. So q is going to be a function of t, okay? That's the thing. Q is not like a number, it's a function. And so in order to solve for it, you have to actually you have to put an integral on each side. You have to integrate each side, okay? And so let's go on to the next page here. So that would be integral dq over q minus ec equals. And then when I do the integral on this side, I'm going to take out the constant stuff, right? So all I'm doing is integrating both sides. After I do that, I'm going to make these definite integrals. So the time, that's an easy one. Time goes from 0 to t. I'm just using that symbol. Okay. By the way, let's just do that one. That's the world's easiest integral, right? There's nothing in there. So this whole thing just becomes, all of this just becomes t. It's equal to t, right? So what I end up with on this side is 1 over RC times t. Yay. Now on the other side, what are my endpoints? Well, I'm going to go from 0, because the capacitor doesn't have any charge initially, but I'm going to go up to big Q. Okay. And you can show, I guess, by substitution is probably the best way to do it. You could say, well, look at all this stuff down here, right? Call that S for Schultz, whatever. And if I do that, I can actually say, well, my ds is simply going to be this, the derivative with respect to q. It's just dq. That's really nice, because it allows me to rewrite that integral as ds over s. And then my endpoints change, right? So instead of 0, I got to put that into here. So that's going to be 0 minus EC. And up here, for the top part, it's going to be Q minus EC. See what I'm doing there? So substitution. This is substitution. Good review. We've done it before. Okay. And then you carry it out. Okay. So what is the integral of 1 over s? Right. Well, that's the natural log of s, but you have to evaluate it between these two limits. You know what? I'm going to take out that 0 because I don't need it. Okay. And then you proceed. I'm not going to write the right-hand side because I don't need to. It's still there. And so I would do natural log of Q minus EC minus natural log of minus EC. And you have to remember that when you subtract logs, it's the same thing as the natural log of the quotient. Now watch your negative signs here, right? Because there was a negative sign right there. I just circled it. So if you want to, you can get rid of that. Just factor it out by flipping the top part of this. And then I will copy down what we had before. Okay. So I'm almost done, believe it or not. I've now solved the integral, and I have an algebraic expression, which looks a little bit ugly because it's got kind of a natural log in it. But it's really easy to get rid of that natural log because you can exponentiate both sides of the equation. That means you can raise both sides to the e power, right? Now remember, if you have like natural log of x, if you raise e to the natural log of x, that's simply equal to x, right? So I'm going to raise the left side to x, and I'm going to end up with EC minus Q over EC. So that simplifies life, right? But if I did that, then I also have to exponentiate the other side, and that exponential sticks around, right? And I end up with negative t over RC. Hey, look at that's, you can see now where that negative RC came from. And so now we're really close to our final answers on this, our final functions. Okay. I goofed up one thing here, and this is a mistake that I made. Sorry about that, but the thing I goofed up, let me do this in purplish stuff here, is that I really should have made this lowercase q. Yeah, because that's not the final charge at the end of the day. That's like the charge at any given time. So go ahead, I'm going to just circle those. It's probably a good point to make here, right? Wherever I circle this q, replace it with a lowercase q. Yeah, sorry about that. And in fact, I'm just going to erase this last line here, and I'll make that a lowercase q, because that's a function. That's the function we want. This is what we want. That's the function, right? It's a function of time. So we just have to get that by itself. Sorry about that little switcheroo there. So do a tad bit of algebra. You're going to have EC minus Q is equal to EC times the exponential of negative t over RC. And then you'll have, you subtract off the EC, of course, right? This has to be subtracted, but then there's also this negative sign here, so you multiply both sides by -1. So doing that in one step, I'm going to get this. EC minus EC, like that. So take a second, be okay with that, algebra. And then once you're good with that, recognize that you can factor out EC to get that expression. I'm going to draw a box around this. And that is actually what we wanted to show. If you remember that, that's our function for charge, which was up here. Okay. So that is how you get this function for charge as a function of time. And look at the time is in there. Again, here's t. And again, your RC is built into it. You're dividing it. And again, think about this term out in front, e times t, that's really kind of like your big Q, the Q final, right? So now that gives us that graph that we expected for Q versus t, all right? To get the other functions, it's super easy. No more calculus is needed. To find the voltage across the capacitor, you simply do, again, let's remember, Q is equal to, I'm sorry, C is equal to Q over V. That means V is equal to Q over C. And so, hey, if I do that, I take my EC and I divide it by C, right? So charge, this is charge from up above divided by capacitance, right? Charge divided by capacitance, that gives me voltage. Cancel, cancel, times stuff, that gives me E to the 1 minus E to the negative T over RC. So hey, that's super easy. So that's your function that tells you that the voltage also does that sort of a dance. Okay, and so just dividing out the capacitance. Okay, so that's a thing. Box it. And the last one for current, Well, current is actually the derivative of charge with respect to time. And this is easy calculus, because you take the derivative of this first expression, which is EC minus EC. Okay, and I distributed out the EC because, you know, if you take the derivative of a constant, you get 0, right? And the other thing is if you take the derivative of an exponential, you get the exponential back. And so that's going to work out for us, right? Because you'll end up with negative EC over negative RC. C's cancel, negatives cancel, and then hang on one sec. Hey, I'll be right with you. And then when you get that, E over R, that's going to be your final current. I'm just going to leave it that way because that's the way we want to probably write it here. So this will just be E over R, e to the minus t over RC. Okay. So again, this expression here is going to be kind of the initial current. I might have said final, but I mean initial. And that's the current that you get when it's basically the Ohm's law current when you first close the circuit. So again, so that final result was gotten with a little bit of calculus. The one before it for voltage was algebra, and the charge one is the one where you really have to do the calculus. You've got to separate variables to get that. Okay. All right. Hope that made sense, and we'll check in.